Hello, in this video you're going to need your calculator as we discuss reaction orders. So again, let's consider a generic reaction, A plus B going to C, and we have this thing called the rate law or the rate equation. We have the reaction rate, that's the change in concentration divided by change in time, that's in units of molarity per second, that's the usual thing. Now that's equal to K times A in brackets, right? To the nth power times B to the mth power. Now, what do these things mean? Well, rate is the reaction rate in molarity per second, okay? And K is the fundamental reaction rate constant, and it only depends on the reaction and, of course, the temperature, okay? N is what we call the order of reaction with respect to that chemical A, or reactant A. And M is also the order with respect to reactant B. So if you have two things reacting, or three things reacting, or four things reacting, you might just have two or three or four different orders with respect to each of the individual reactants. Okay? Now, N plus M, if you add up all the individual orders, you get something called the overall order, or the total order of the chemical reaction. All right? So the rate law is a rate equation that is valid for any concentration. So you could plug in different concentrations and see what the rate is, okay? And that's an instantaneous rate. We can do that for many different reactions, and I'll show you how that works. All right, now first of all, I want to give you some cautionary tales here. The orders are usually whole numbers in general chemistry, okay? And we're going to deal with 0, 1, or 2. All right, pretty simple. And the orders do not come from the balanced chemical equation. Now, I talked about the relative rates and the instantaneous rates and how you had to use coefficients in the balanced chemical reactions. Well, this is something else. We're calculating orders, and this comes from reaction data or experimental data in the lab, Lab 4 if you're in my class. All right, so let's look at the overview of the steps to determine the reaction order. First, you need to find an experiment where only one reactant is double another. Now here, I just want to pause for those of you not in my class taking chemistry from elsewhere. In the OpenStax textbook and many other textbooks, they give you very complicated concentrations where the reaction is not exactly double another reaction, okay? So you have to use the ratio of logs and all this business. I'm not into torturing my students like that, okay? So what I'm showing you here are three simple steps exactly utilized when you have a concentration that's perfectly doubled. And why not make it simple? If I was doing an investigation in the lab, I would make one concentration 0.1 molar, and I would double that and make another concentration 0.2 molar. I'd measure the rates, and I would very easily just calculate the ratios. Okay? So in my class, find the experiment where one reactant is double another. Then you want to find the ratio of rates. It's always going to be the higher divided by the lower. And then you're going to use the table to determine the order. And this is your lookup table. Okay, you don't have to do ratio of logs and find out if it's 1, 2, or 4 and all that. If your ratio is 1, your order is 0. If your ratio is 2, the order is 1. If your ratio is 4, your order is 2. Okay? So we'll go through all of this, and I'll hopefully explain these ratios in the following examples. And usually students have difficulty getting data from tables. So I'm going to spend a lot looking at these tables, okay? So let's look at a chemical reaction. Methanol is producing this thing called CH3 dot plus OH dot. Don't worry if you're not familiar with this symbolism. This is a chemical reaction, okay? And the first step is usually to find an experiment where only one reactant is double another. Here we only have a pair of experiments, so only one reactant. And we just skip this step, okay? So step 2 is to take the higher rate and divide it by the lower rate. And you can see from the table, we want to take the 5.6 divided by the 2.8 times 10 to the minus 4s, and we get a ratio of 2. And then what we do is we look up the order in our little table here, the cheat sheet, so to speak. So if my ratio is 2, I look to the right, oh, the order is 1. So therefore, we can now write a rate law or a rate equation for this chemical reaction. And here I'm leaving the first power written so you can see that it's present. but we normally simplify our rate law and just write rate is equal to K times methanol concentration, okay? Now, what does this mean physically? What's going on here? Well, it means that if we double the concentration of CH3OH, we're going to double the rate, okay? And we can see this in the table. If we look at the concentration here, we're doubling it. It's going up exactly by 2. And if we look at the rate, we can see that we're also doubling it. It goes exactly by 2, okay? And that's something that's raised to the first power, okay? Now, let's look at another reaction. Here we have nitrogen dioxide reacting with some reaction data here in this table, okay? And step 1, usually, again, we can skip this step because we just have two experiments, all right? Step 2, we want to find the ratio of rates. Now, you always want to make sure you have the higher rate and divide by the lower rate. In my classes, like I mentioned, the rates will always be 1, 2, or the ratios will always be 1, 2, or 4. And in the lab, you're going to have to round to the nearest of these values. If you do it wrong and you do it the lower divided by the higher, you're going to get like 0.5 or 0.25 or something, and this is not what we want, okay? So our ratio here is rounded to 4, okay? We want to use the lookup table here. And again, don't skip step 3. Some students say, oh, 4 is the answer. It's a 4th order. The ratio is 4, and this corresponds to an order of 2, all right? So now we can write the rate law, and we can see that we have an exponent of 2 operating on the concentration of the NO2 gas, okay? So this is a 2nd order reaction. So what happens if we double NO2? If we square a doubling, this gives us an increase of 4 times for the rate, and we can maybe more easily see this feature from the rate law expression having the power of 2. So if we take the concentration and we double it, we can see that the rate actually goes up by times 4 because we're squaring that term. In other words, if you take 1 squared versus 2 squared, you can see you're going from 1 to 2, which is a doubling, but because you have that squared term in there, you're actually going from 1 to 4. So you increase the rate by 4 times when you double the concentration. So hopefully the algebra makes a little bit more sense, okay? Let's look at our final illustration here. Again, we have just 2 experiments, so we skip step 1 again. And we want to find the ratio of rates. Here it's like trivial. There is no higher or lower. You do the ratio and it's like 1. Is that right? Is that possible? Yes, it's possible for the ratio of the rates to be 1, and that's why it's in this table. The order is going to be 0. And what that means is that the rate law becomes simply rate is equal to K times CH3 to the 0 power, which means it's 0th order or 0 order with respect to methanol. And because anything raised to the 0 power is 1, the rate equation simplifies to rate is equal to K. And what that means is the rate is independent of CH3OH concentration. You can double it, you can triple it, you can halve it, and the rate's just going to be the same. All right? Okay, let's do a typical type of problem you would expect in my chemistry course or your chemistry course that you might be taking. Here we have 3 reactants, A, B, and C, and various rates that correspond to different experiments, okay? Now in this problem, we actually want to find the value of K, but before we do that, we have to figure out all the orders. And again, I just want to mention that I give very simple data where it's obvious where one concentration is double the other, okay? I don't try to give crazy numbers that you have to do ratio of logs. So step 1 is to find an experiment where only one reactant is double another. So in other words, we look for a pair of experiments where only one thing is changing. So let's try to do this where A, the reactant A, is changing first, okay? So you hunt around and you want to find an experiment where the only thing changing is the concentration of A. I'll highlight these 2 experiments. So in experiment 2 and 3, the concentration of B and C stay the same. The only thing changing is A. So when we analyze the ratios, we're going to get information about A. All right? So we calculate the ratio of rates shown here in this blue box, and that tells us something about the reaction order with respect to A. And we're going to go ahead and do that here, okay? So the ratio is 2.32 times 10 to the minus 2 divided by that same number, which is 1, all right? Again, we want to look up the order, and I didn't put the table here on my slides, but that's 0 order with respect to A. So I'm just going to jot this down in the upper left-hand corner for later use and referral, okay? So let's do the same thing, but now look for a pair of experiments where only B is changing. And this is where students have a little bit of difficulty, all right? I've found it. So if you look at these two experiments, experiments 1 and 2, the concentration of A is the same, the concentration of C is the same. The only thing different is the concentration of B, all right? So I'm highlighting that for your notice here. So this is a suitable pair of experiments where we find something about the concentration of B and the order of B, all right? So what you want to do now here is find the ratio. So the ratio is the higher number divided by the lower number. That's equal to 4, all right? And then you want to look up that order, and the order is 2, okay? So this is a second order with respect to B. Again, I'll jot that down in the upper left-hand corner for use, okay? All right, now what we want to do is analyze this table for finding a suitable pair of experiments that tell us something about the concentration of C changing, all right? And what you want to do is very carefully look, because you want the concentration of A to be the same and the concentration of B to be the same in the two that you select. I've found two. In experiments 3 and 4, only the concentration of C changes. B is the same and A is the same, okay? So you got to hunt around for it, and even make a box or something like that if you're doing this on scratch paper, okay? So I've highlighted the experiments I want to analyze. Again, we want to take the ratio of rates. So we want to take the higher rate, which is 4.6 times 10 to the minus 2, divided by the lower rate, and that's about 2. Remember, we want to round it to 1, 2, or 4. This rounds to 2. And then when you look it up on the order table, it comes out to be first order with respect to C, all right? So the order is 1 with respect to C, all right? So now that we have all our orders for all the reactants, we can write the rate law or rate equation and possibly simplify things, okay? So the rate law is rate is equal to K times A to the 0th power, B to the 2nd power, C to the 1st power, right? So the 0, 2, 1 are the individual orders, as we talked about. Now anything to the 0th power is 1, so we can just erase that term. And anything raised to the 1st power is just the number itself. So we can simplify the rate equation to rate is equal to K times B squared times C, all right? So that's the rate law. Now we can finally answer the question, determine K. So how do we determine K? Well, first, what you need to do is solve for K, all right? So K is equal to rate divided by B squared over C squared, so that's just algebra there, okay? And then what you can do is you can use any experiment to plug in and evaluate K. I just typically use experiment 1 because it's easier for my eyes to pull out the numbers from the top of the table to enter into the equation. And you will want to make sure that you cancel units here, okay? So molarity, one of them cancels, as I'm showing here in the animation, okay? And so you're going to be left with seconds to the minus 1. And in the bottom, you're going to be left with molarity squared, which is inverse molarity squared. And so what I'm going to do is write it out like this. 3.7 times 10 to the 2, molarity to the minus 2, seconds to the minus 1. Okay? So here's the final answer. You're going to be doing something similar in the kinetics lab. There we will have 2 reactants, not 3 like this example. But you should not write A and B because we actually know the chemical reaction and substances involved, which are potassium permanganate and oxalic acid, okay? The hardest part of this is looking at the table and pulling out values. Please check my Stoddard Tutoring YouTube channel for more videos that work through just problems from textbooks. Thanks for watching. Please like, please subscribe. I hope this video helped you.